Okay, so in the previous classes, we discussed about DC bridge circuits and some techniques to measure resistance of high range. Now, in today's class, we are going to discuss something about AC bridge circuits uh, as a means of measuring unknown inductance or capacitance and unknown frequency. So, if we talk about the basic AC bridge circuit, so the form of the circuit is actually similar to Wheatstone bridge, but as we are dealing with AC quantity or AC source, so instead of resistance, we have to consider impedances in all the four arms. And similarly, what is done with respect to some known quantities? Suppose if this is our unknown arm, we would try to determine the values of the inductance or capacitance or the total impedance connected in this arm by varying some of the other impedances and achieving the null deflection in this detector. So the basic balance equation is also similar. However, as we are dealing with impedances, now the quantity associated will be a complex quantity. So this bar I am using to indicate the quantities to be complex numbers. Now from here we can easily say that the balance equation will be the one that I am writing over here, which is quite similar to Wheatstone bridge, but in terms of impedance. Now, as we are dealing with impedances and they are complex quantities, so they are definitely going to be associated with, or we can represent them in terms of their magnitude and respective angle. So this balance equation, we can also rewrite it in terms of the magnitude and in terms of the angle separately. So in terms of magnitude, we can consider the balance equation to be in the same multiplied form, but when we want to establish the relation between the angles, as they are complex numbers. Now when we are multiplying, the angles are supposed to be getting added, so the relationship between the angles should be this one. And similarly, what we have done over here, if it is for the circuit analysis, if it is necessary or it is useful to represent the balance condition in terms of admittances, then we can also do that. If we convert each of the impedances to their equivalent admittances by taking the reciprocal, then we can also represent the balance condition in terms of their respective admittances. And after we convert to admittance, if the associated angles are phi, then the relationship between them will also be similar. Now, before going to a specific bridge circuits or different variations of the bridge circuit, two other terminologies I want to discuss that will be associated with the later discussions. So one is the quality factor. Quality factor Q. Now, the quality factor of an impedance, we can represent it as XS divided by RS. So suppose if we have a resistance connected in series with an inductor, then its impedance we can represent at R plus J omega L, where omega L is the reactance of the inductor and R is the resistance of the resistance actually. So as they are connected in series, so this is actually the equivalent series combination between the resistance and inductance. And also if they are connected in parallel, we can take the parallel combination and represent them in terms of in this format, actually a summation of a real part plus an imaginary part. Then we can say that the real part is the equivalent series resistance and the imaginary part will be the equivalent series reactance. Now the quality factor is actually defined as the ratio of the equivalent series reactance to the ratio of equivalent series resistance. Now, what does the quality factor signify? Do you guys have any idea? Maybe you guys have studied it in your circuit course.
Yes, sir.
So can you give some idea about it?
As far as I know, it's a triangle with reactance power in one axis and real power in another axis.
Okay, yes, in a sense it is a comparison between the powers. Now, one is the power which is getting stored and another one is the power which is getting dissipated. So you know that inductance, capacitance, these are energy storage elements. So they are going to store the power, and the resistance is an energy dissipating element, or they will dissipate energy or absorb energy or power. So actually the quality factor will indicate how much power will be stored or how much power with respect to how much power is getting absorbed. For example, the power stored in the reactive element, you can say it is I square XS, and the power stored in the dissipated in the resistance is I square RS. So if you take the ratio of these two, then you will have the I square to be cancelled out, because for the equivalent series combination of any particular connection between resistance or inductance or capacitance, the same current will flow through the equivalent series combinations. So it is actually giving you a measure of how much power is actually getting stored compared to how much power is getting absorbed. Now, on the other hand, it is also giving us a measure that how much reactive the impedance is. So whether the reactive part is more dominant or the resistive part is more dominant. If the value of XS is very high compared to RS, then you will have a higher quality factor. So you can say that the impedance is more reactive, or the reactive part is more dominant. On the other hand, for a low quality factor, you can say that the resistive part is more dominant. Now, with respect to that, another factor is always often considered, that is dissipation factor. So that is nothing but the reciprocal of the quality factor, and it is RS by XS. So that is, if we obtain a higher dissipation factor, then we can say that the impedance is more resistive. And if we obtain a lower dissipation factor, then we can say that the the resistive component is less dominant in the impedance or equivalent series combination of the impedance. So let us keep these terminologies in mind. Later on, we will again come back to this, quality factor. So now the first variation of among the different types of AC bridge circuits, the first one that I'm going to discuss is the Maxwell bridge. And you can see that now, compared to the basic AC bridge circuit, it is also in similar format. However, we have defined the Z1, the impedances, in terms of the different combinations between resistance, inductance, or capacitance. So this is our unknown arm, where we have put an inductor LS in series with a resistance RS. Now, this might not be a physical resistance connected in series with the inductor. However, it could be the parasitic resistance that is present in LS, because we cannot create any inductor or capacitor that is 100% inductive or capacitive. Some parasitic resistance will not be there, will be there. So this RS might not be a physical resistance connected in series with the inductor. However, it can be only the parasitic resistance that is present in LS. So this Maxwell bridge is actually designed to measure unknown inductance. Now, apart from this unknown arm, in place of Z2 we have a resistive component R2. In place of Z3 we have another resistive component, that is R3. And in the first term we have a series or parallel combination of R1 and C1, I mean a resistor and a capacitor. And you can see that both R1 and C1 are variable resistors. So we have to tune these two resistances to obtain the null deflection in this detector. Now, in order to obtain the balance condition, we can start with the basic form of the balance condition and then put the expressions of different impedances in the balance condition and try to simplify to get an expression for RS and LS. So in order to do that, let us first define the impedances in all the four arms. So if we consider Z1, so in Z1 we have a resistor connected in parallel with a capacitor. So let me give a bar over here to indicate the complex quantity. Now we can say that this resistance R1 is connected in parallel with the capacitive reactance. So if we take the parallel combination, what we will get, now we can multiply both the numerator and the denominator with j omega c1, so that we can further simplify this expression. So on the numerator we'll have R1, and in the denominator we will actually have 1 plus j omega R1 C1. Now if we put this expression directly in the balance condition, it will be difficult for us to simplify uh, in terms of RS and LS. So what we can do, we can convert this Z1 into its equivalent admittance so that our simplification becomes easier. So let us just convert it here and we'll see the balance condition later on. So just the reciprocal of this one. So if we take the reciprocal of this Z1, we will have 1 by R1 plus j omega C1. And for Z2 and Z3, it is nothing, just we have two resistors connected in these two arms. And lastly, the unknown arm Z4, we can define it in terms of the series combination between the unknown resistance and the inductance. So once we come up to this point, then we can refer to the balance condition and put each of these impedances in the balance condition and simplify to get expressions of RS and LS. So the balance condition, let me write it over here again. Now I can easily take this Z1 on the right hand side and 1 by Z1, which will actually give me the admittance. So my left hand side, it is nothing but RS plus j omega LS, and on my right hand side Z2 and Z3 is just resistive elements R2, R3, and in place of Y1 I can put this 1 by R1 plus 1 by R1 plus j omega C1. After I do so, now I can keep my left hand side as it is. I can simplify the right hand side. In this case, it is pretty straightforward. Just I am multiplying this term with this, and now both my left hand side and right hand side, I can equate the real and imaginary parts. So that will be sufficient for us to get the expressions of the unknown quantities in terms of other circuit parameters. So in this case, Rs would be equal to R1 into R3 by R2 into R3 by R1. And equating the imaginary terms, we'll have Ls equals R2, R3, C1. So these are the expressions that can be used to determine Rs and Ls. Now, from these two expressions, we can see that Ls is actually dependent on only one variable resistor, R3, whereas Rs is dependent on both the variable resistance, R1 and R3. So using this bridge, obtaining the balance condition is slightly difficult compared to the DC bridge circuits, because we have to tune two different resistances to obtain the null point. So using the two different resistances, I mean tuning one resistance at a time and then tuning the another. So for both the cases, there will be some mismatch. So one or two or three iterations might be necessary to obtain a point where both the resistance are adjusted properly, so that the balance condition is obtained. Now, these are the two expressions. Now, we will use these two expressions further to find the expression for the quality factor. So, yes.
This configuration of capacitor and Ls constitutes Maxwell bridge, right, sir? This particular configuration.
I mean, this particular configuration was proposed by, suppose, Maxwell. So that's why this is fixed for this particular bridge. Okay.
Sir, is there any physical significance of this particular bridge?
Physical significance, I mean, the physical significance, I mean, how the scientists came up with this particular combination, that I don't know. But maybe he had done it through a different experimental trial and error method. But once he has obtained this particular combination to be working for the determination of the unknown inductors to be quite effective, maybe from then on it was considered to be accepted universally. But at this moment, I don't actually know whether there was any physical significance which was observed.
No, sir, what I mean by this, that are there any relatable application of this bridge?
So is there any other combination for AC bridge, like if I don't use the capacitor, or I use inductor in there, or I can use the resistor R1 in series with C1, like this? Any other combination?
Yeah, obviously there are other combinations. Now there is some problem in this bridge. For that, later on, other I mean combinations were also proposed. So suppose here he proposed this particular combination where he has connected a resistance R1 in parallel with C1. So this actually causes some problem. So to eliminate that problem, later on another circuit was proposed. So that is called the Hayes bridge. So I'll go to that bridge circuit a little bit later. Okay. So before going to that circuit, okay, let me discuss about what is the problem if this particular combination is used, or when this particular combination will be useful, and when this particular combination will cause us to deviate from the expected result of the unknown inductor. So before going to that portion, I should discuss about the quality factor. So the quality factor, which we discussed at the beginning of the class, has to be the ratio between XS and RS, the equivalent series reactance and series resistance. So the XS, I can write it to be omega LS, the magnitude of it, and RS, I can keep it like this. Now, instead of RS and LS, we can put these two expressions that we have found over here. So if we put these two expressions, then what we will end up with is omega R1 C1. So using the values of R1 and C1, we can determine the quality factor, and also using the measured values of RS and LS with respect to the known frequency, we can determine the value of the quality factor. Now, as we are talking about quality factor, now if the quality factor is high, then the unknown arm is more inductive. If it is in medium range, then it can be referred to be as a combination of both a resistive part and an inductive part. And in case of low values, suppose when Q is less than 1, it can be said that RS is more dominant compared to LS, or it is more resistive. Now the problem of this particular bridge circuit is in measuring high quality factor inductors. Inductors which have high quality factor. So what is the problem that can be actually discussed in terms of the balance equation, which is defined in terms of the angles, which is theta 1 plus theta 4 equals theta 2 plus theta 3. Now, what do we expect to have on our right hand side? Because theta 2 and theta 3 associated with these resistive elements, their corresponding associated angles will be 0. So we are supposed to have 0 on our right hand side. And as we are talking about the case of high quality factor inductor, so for this unknown arm, XS is supposed to be very high compared to RS, or it is more close towards to being a purely inductive branch. So in that case, what should be our angle? Theta 4.
90 degrees.
It should be plus 90 degree. So if we want to balance both sides, the angle of theta 1 should be set, or the values of R1 and C1 should be tuned in such a way so that theta 1 gives me almost minus 90 degree, so that this will counterbalance this inductive arm, and we obtain a balance between the two sides. However, when they are connected in parallel, in order to make this parallel branch more capacitive, the value of the resistance required would be very high, because as they are connected in parallel, suppose let me denote the capacitive reactance here by XC1. So if we want to make it more close to xc1, then what we need to do, we have to make this value or set this value to a very large amount, because after that when we are going to, when this value is very high compared to this one, then the equivalent I mean impedance will be more towards, close towards xc1, because for any parallel combination, suppose you have, if we consider two resistances, 4 in parallel with 2, if you take this parallel combination, it will be actually closer to, the equivalent value will be closer to 2. If you take 8 parallel to 2, it will be even more closer to 2. So when we are taking a parallel combination between two elements, the equivalent impedance or resistance, whatever you say, that would be more close towards the lower quantity. So for this particular combination, in order to make this branch more capacitive, a very high value has to be set for resistance R1, but practically variable resistors of very high range is not available. So this particular combination becomes, I mean, this becomes a negative feature for this particular combination, because when implementing it practically in terms of for determining inductance with high quality factor, due to unavailability of very high range potentiometers or variable resistors, this limits the use of this particular bridge in case of high Q value of a inductor. Now, in case of medium inductor with medium quality factor, now this angle is not supposed to be exactly, or I mean almost equal to 90 degree. It will be some intermediate value. So if this is the real axis, this is the imaginary axis. So when the inductive part is dominant, we can define the impedance to be aligned with the imaginary line, and when it is close, more resistive, we can align it to be on the real axis. However, when there is combination of both of them, it will be in some intermediate stage where the angle is not in between 0 to 90 degrees. So in that case, suppose for 45 degree, using a combination of R1 and C1, this angle of minus 45 degree might be obtained for medium values of Q. So, but for high Q value, it becomes problematic for unavailability of very high range potentiometers. Now, using the same circuit for the determination of inductance with low quality factor also becomes sometimes problematic due to a problem which is termed as balance of convergence problem. What is the problem? You can suggest that in order to obtain the balance condition and to converge to a null deflection for this particular circuit with low Q value of inductors, it will become a problem. Why the problem will arise? Because like we have already defined the unknown resistance and inductance. So here we can see that or already what is discussed, that the resistance is dependent on both R1 and R3, whereas inductance is dependent on only R3. Now for medium range Q, both RS and LS are comparable with each other, and by varying R1 and R3, tuning them with after two or three trials, maybe we'll obtain balance condition. But for low Q values, RS is more dominant because the element is more resistive compared to the previous case. So as LS is small, when you are trying to adjust LS in terms of the variation of RS, as R3, as RS is having the significant effect here, slight variation of R3 might significantly affect the convergence in terms of RS. So several trials has to be done in terms of R3 and R1 to find optimum case where there will be almost zero deflection in the bridge. So tuning both the resistors to obtain the null deflection becomes a factor in case of measuring inductances of low quality factor using this particular bridge circuit. Now, by slightly modifying this bridge, this particular problem of measuring inductances of high quality factor can be reduced or eliminated. So by this time, maybe you can already suggest, because the problem is being created by the connection of the resistance and the capacitor being connected in parallel. So if we connect them in series, then we will not require a potentiometer which has to be of very high value. So using a low valued potentiometer, then it can be ensured that the angle of this branch is close to minus 90 degree. So based on this fact, this Hayes bridge was introduced, where in this Z1 arm, the capacitor C1 was connected in series with the resistance R1. So in this case, the resistance doesn't have to be of a very high value, and easily the balance can be obtained for inductance which also have high quality factor. Now, to determine the balance condition for this particular bridge, Hayes bridge, we can follow the same process that we followed in case of the Maxwell bridge. Now I can denote over here that this bridge is more useful in case of high quality factor inductance compared to the Maxwell bridge. Now, if we proceed with the evaluation of the balance condition, we can first determine the impedances like we did in case of the Maxwell bridge. So we can define the impedances first. So Z2 and Z3 is same as before, two resistances connected in the two arms. And for Z1, here now it is a simple series combination between the resistance and the capacitor. So as they are already connected in series, we are not going to convert it into the equivalent admittance, because we can easily simplify the balance condition with this format. And for Z4, we have RS plus J omega LS. So from here on, if I rewrite the balance condition, So we can keep Rs plus j omega Ls on the left hand side, try to simplify the expression on the right hand side, and then similarly as we did for Maxwell bridge, we can equate the real and imaginary quantities. So to simplify the right hand side, we can multiply both the numerator and the denominator with the complex conjugate of what we have in the denominator. So let me do it on the next page. So as we are multiplying by the complex conjugate, we can easily simplify the denominator here, and we can go on with the process of simplification. The j square can be easily replaced with -1, and now both the numerator and the denominator can be multiplied with omega square into c1 square. So what we will have, so from this point onwards, we can separate the real term and the imaginary term and equate it with this left hand side. So the expression for Rs can be written as omega square c1 square r1 r2 r3 divided by 1 plus omega square minus r1 square c1 square. And for Ls, it would be omega c1, sorry, omega will get cancelled out. This, so these would be the two expressions for the two unknown parts of the unknown arm. Now with respect to these two equations, these unknown parameters can be determined. However, in case of Maxwell bridge, these two expressions were independent of the uh, frequency of the signal. However, while uh, while using this particular bridge, the frequency of the input signal is actually works as a factor for both the quantities. Now, the quality factor of this particular quality factor of the inductor for this particular bridge can also be defined using these two expressions of Ls and Rs. So if we use these two expressions, we can define the quality factor to be one divided by omega R1 C1. Now, the expressions for RS and LS can also be represented in terms of the quality factor. So, okay, let me rewrite the expression for RS first. Now, for the LS, we can rewrite this whole expression in terms of the quality factor to be C1 R2 R3, and the quality factor is actually nothing but the reciprocal of this term, so we can write it as 1 by q square. And for RS, we can divide both the numerator and the denominator by omega square R1 square C1 square. Then by doing so, we can again express RS in terms of the quality factor. So this 1 by omega square R1 square C1 square would actually give me q square plus 1. So as for this particular circuit, we are talking about inductor that has a high quality factor. So for that, we can further approximate these two expressions to rather a little more simpler form. So that would be for RS, if as q, the value of q is greater than 1, so the value of q square will be even greater. So RS can be written as R2 R3 divided by q square into R1. And for LS, as the value of q is very high, 1 by q square will actually give us a value that is very close to 0. So for this one, the expression of LS can be defined as the multiplication of C1, R2 and R3, which is actually same as the expression of what we got in case of Maxwell bridge. So while we are dealing with inductor of high quality factor, the value of the inductance can be measured using the same equation that was also determined in case of the Maxwell bridge. So irrespective of the signal frequency, if the signal frequency is not known, still for high quality factor inductor, the value of the LS can be determined in terms of these known values of C1, R2 and R3. So regarding these two bridge circuits, is there any question, anyone?
So in Hayes bridge as well, we will have problem with low quality factor inductance, right?
Yeah, actually that problem sustains in both the bridges, and it will sustain actually because whenever we have multiple potentiometers, it would be, or multiple variables, it will be difficult to adjust both of them. Even in case of DC bridge circuit, suppose there are 4 resistive arms. Okay, so normally what we do, we vary only one, right? But what if we want to vary 2 resistors? Suppose 2 are fixed, but for some reason we need to vary both R and S to obtain the null point. So that would be difficult to obtain, right? I mean, varying both R and S, tuning them
Yes, sir.
at a point where we are getting the null deflection. So similarly here as well, as these are dependent on multiple variables, so there will be some problem in tuning them, especially when the value, I mean, the inductor or capacitor are having a low quality factor, the resistive part is dominating, because the effect of both these resistances, R1 and R3, is on RS. So RS, if RS is more dominant, the effect of varying both R1, R3 and R1 will have more effect on RS. If it is less, then the effect of varying both the quantities will also be less, because the other quantity is dependent on only one variable. Now, those were 2 bridge circuits in order to, I mean, measure unknown inductance. Now, in order to measure unknown capacitance, another bridge was proposed, which is called the sharing bridge. Now, in this bridge, in the unknown arm, there is a series combination of capacitance and resistance. Still, in this case, this resistance is mostly, it can be considered to be the parasitic resistance that is present in CS. And for the, I mean, rest of the arms, in Z2 there is a variable resistance, in Z3 there is a capacitor, and in Z1 there is a combination of parallel combination of R1 and R3. So I will let this the derivation of this particular bridge as a task for you. I think you can do it because the process is actually same. So I have shown you two of them already. So using the similar process, I mean, you can define what is Z1, then what is Z2, Z3, then Z4. You define the impedances first, then put the expressions in the balance condition, then equate the real and imaginary parts to get the expressions of RS and CS. So I think you can easily do that. Now, in the book for all the bridge circuits, so I am covering this portion of AC bridge from chapter 5 of the writer MMS Anand. So in the book, you will find that for all the bridge circuits, the author have only given the, I mean, the expressions of RS and CS or RS and LS directly. So you, following the same process, step by step, you can easily derive the expressions by yourself. So I hope that you can do it by yourself. So I'll leave that to you. Now, lastly, today I'll discuss another bridge circuit that is for measuring unknown frequency. It can be used for measuring the signal frequency. If the signal that is being transmitted over here into this bridge network, if the frequency of this signal is not known, then that frequency can be determined in terms of the circuit parameters. Now, this source could be a signal from any transmitter, So a unknown signal is coming. Then after tuning the resistances, when you obtain the null deflection in terms of the values of the resistance and the capacitances, the frequency of that unknown signal can be determined. Now for this bridge as well, we can follow the similar process that we did previously by defining the impedances and then further simplifying to have an expression for the unknown frequency. So let us try to do that now. So as R3 and C3 are connected in parallel, so we can, after defining the impedance, we can take the admittance so that the computation or evaluation becomes easier for us. So similarly, what we did for in case of Maxwell bridge, when there was a series, there was a parallel combination, we can write the Z3 to be in this form, and correspondingly the admittance will be 1 by R3 plus j omega C3. And for the last 4 term, we only have a resistor. So now we can combine all these terms together in the balanced equation to obtain the uh, expression for the frequency omega.
Sir,
Yes.
please can you go back to that slide? I want to see that one. Okay, sir, you can move. Okay, sir, it's okay.
Okay, so if we put in the balanced equation, so while simplifying the balanced condition, now we are not considering any one of the arms here to be unknown, because or any inductor and capacitor that we need to measure. Rather, we want to measure the unknown frequency. So I'm not going to keep anything, consider any one of these branches to be the unknown branch to keep it on one side. Rather, here the approach would be to keep the resistive, purely resistive parts in one side and the complex parts on the other side, and then after simplifying to compare the both sides to, I mean, equate the real part and the imaginary part. So on my left hand side, I can write it to be Z1 into Y3 when I representing the Z3 in terms of its admittance. And on my right hand side, I can have Z2 by Z4, which is actually R2 by R4. Now, for the left hand side, now let us go deal with the imaginary quantities, complex quantities. So on the left hand side, I can combine the real parts and the imaginary parts separately. So straight away, by comparing the left hand side and the right hand side, I can have the relationship between the 4 resistances and the capacitances to be R2 by R4 equals R1 by R3 plus C3 by C1. So equating the real parts. However, on the right hand side, we don't have any imaginary parts, so we can equate this portion associated with J to be equal to 0, and we can further simplify in order to have an expression of omega. So from here, we can set it to 0, or we can say that these two quantities are equal. So we'll have omega square to be 1 by R1 R3 C1 C3. So that will give us omega as in terms of the values of R1 R3 and C1 C3 if we take the square root of this multiplication. And this is the angular frequency. Now the frequency in terms of hertz, we can also derive that or find that by just dividing simply by twice pi. Now either of these two expressions can be used to determine the unknown frequency. Now furthermore, to simplify the process of the calculation, oftentimes while designing the circuit, the values of C1 and C3 are kept to be equal. That is, C1 equals C3 equals suppose a same value for these two, which we can represent here to be C, and the R1 and R3 are also varied in such a way that both of them are, the variation in both the resistances are equal. So suppose there are two potentiometers. This is the slider of one. Suppose this is R1, this is R3, and this is the slider of the other variable resistor. Suppose both of them are 10K, and if these two sliding arms of both the variable resistance can be coupled together, then whenever the slider is varied, as both of them are coupled together, they will give the equal value of R1 and R3 each time. So in that case, our expression for the frequency, we can write it to be 1 divided by twice pi RC, or R square C square, so twice pi RC. So this further simplifies the calculation, and while we are following these two conditions, another condition has to be followed or ensured, that is the values of, what should be the values of R2 and R4. So because we had a relation between these two resistances R2 and R4 defined in the previous slide. So as we want to keep C1 and C3 equal and R1 and R3 to be equal, then these two has to be adjusted keeping this condition in mind, so that this expression of the frequency can be used. So what should be that condition? That is R2 divided by R4, as both the resistances and capacitances are equal. So the value of R2 should be twice the value of R4. So if these three design rules are followed, then the frequency of the unknown signal can be determined using this simplified expression. So that is the last bridge circuit that I wanted to discuss in this class. So it is for measuring unknown frequency, whereas the other bridge circuits are for measuring unknown inductance or capacitance. And now if you have any question, you can ask about today's lecture. Well, I think maybe there is no question, so I think I can conclude today.
Sir,
Now, yes.
Yes, last week's class with section A, you took the attendance and I couldn't respond despite being present in the Zoom meeting, sir, for some medical issues.
Now, whether it was net issue or you logged in and then you fell asleep, how can I justify that?
Sir, can I call you personally, sir? Not here, sir.
Okay, you can call later. Okay.
No, sir, thank
After
you.
the class. So now, since both section A and section B are here today, so I think both the seers are here, right?
Yes, sir.
Okay, so in my last class with section C, I told the seer to contact both with seer of section B and A to, I mean, set the quiz dates, one at the last week of this month and another at the beginning of next month. So did he contact with any one of you? Or did you guys have any discussion?
Sir, we have had a discussion, but the dates have not been fixed yet. I mean, we are checking the schedule with other courses quiz. Inshallah, we will have a discussion soon, and we'll let you know.
Okay, so let me know by next week. Okay, so fix it by next week and tell me the two dates on which you want to take the two quizzes. So after you inform me the two dates, later on we can sit together and decide the syllabus, or I'll inform you the syllabus for the two separate quizzes. So let's conclude here today, and next week inshallah we'll have our class again.
Assalamu alaikum.
Assalamu alaikum.
Walaikum assalam.
Assalamu alaikum.